welcome everyone. My name is Jonathan. I'm from PCB GovTech Singapore. Right, welcome and for today's events on this EM scanner, jointly hosted by PCB GovTech and our developer from YIC Technology. Right, as the name PCB GovTech, we as a company, the company deal with solution on PCB related and electronics related industry. Right, the company was set up in 1997, so we are in the market for 20 over years. All right, so our location, we cover Southeast Asia, as myself here in Singapore, and we also have offices in Malaysia, Vietnam, and in Philippines. All right, so these are the products that we carry, and today we are coming for this YIC technology, and the rest of the product that we carry are the software that is PCB related, as PCB design software, as Altium, and we have hardware like printed circuit board machineries, and we have CAM software like UCAMCO, you like PCB library. Right, so this is just a short introduction of what our company do. I don't have much to talk about. Yeah, that's all for me. So I'll just hand over to YC as we proceed further to understand more of EM scanner.
Problem with audio. Let me introduce myself. I am Arturo Mediano. I will be in charge of the presentation, the technical presentation. So let me start, and then we will be able to try again with Cornell. Let me share my screen. So I am going to show you several slides. So hopefully now you can see the screen of my computer where I have slides for PowerPoint, and I have some cameras where you will be able to see the experiments I will be doing today. Well, we are going to talk about EMI, EMC design and troubleshooting using near-field probes and scanners, basically scanners. And you can see in the top left of the screen the slides I will be introducing at the beginning. In the top right, you see a picture that is coming from my camera, looking the full laboratory. You can see my scope, it's an RTO from Rodan Suar. This is the spectrum analyzer. I have here the scanner from YIC, where I will be doing part of the experiments. And here in the first line, we can see the EM probe. That is the other model of a scanner that you can use from YIC. And in the top, in the picture that you can see now here in the bottom side right is the picture of the scanner with several PCBs I will be using in my demos. Okay, so let's start. Let's increase the size of the screen here. Let's go here. Okay, in this way, so you can see in full screen. Well, we are going to talk about EMI and EMC, but basically this is a very good topic for any people interested in high frequency. That is, like you can see in the slides, my laboratory is the HF Mic Lab. I am working with YIC from many time ago, and I am very happy to collaborate with them. I am doing some research for the company, preparing the future products of for debugging and for solving problems in EMI. And this high frequency topic is related with interferences. This is what we call EMI. This is related with electromagnetic compatibility, EMC. But this topic is very interesting too for people interested in signal integrity or in radio frequency applications in general. Well, let's start with the introduction. Remember, in EMI and in EMC, we have a problem where some kind of victim will be experimenting problems. This is our victim. Let's start. Let me try with my pencil. Okay. So you can see here the victim, And we have two possibilities to have problems from other products, is to have some kind of intentional transmitter. This is the situation when you have a wireless system, for example, some kind of phone, or you have Wi-Fi, Zigbee, Bluetooth communication in your products, and then part of the energy that you are radiating to the environment is able to arrive to the victim, creating failures. The other possibility is to have unintentional transmitters. Any kind of electronic product can create problems, and this kind of products not necessarily have some kind of antenna.
Il faut aller sur le...
Sorry, can you, okay, please try to mute your microphones. Okay, with the unintentional transmitter, you can create problems in the victim without any kind of intentional antenna. For example, you can have radiation from your PCBs, from your wires, or from the enclosure in general. This kind of problem is related with the distance between the two elements, the frequency that you are using, and the energy that your signals have. This is a typical result from the measurements in a laboratory with a semi-anechoic chamber at 3 meters, where we put an antenna at 3 meters from the device under test, and then we measure in some specific frequency range, for example, in this example, from 30 megahertz to 1 gigahertz, from 30 megahertz to 1 gigahertz, and we have two typical possibilities. Perhaps we have this kind of failure, where we can find this kind of, how to say, mountain, no? We are failing in this area. Let me try if I can use the pointer. We are failing in this area, where you can see that close to 100 megahertz, I have 10 to 15 dBs over the limit. The limit is the line that is in red color. And the other possibility is to have this kind of profile where we have emissions, or we have a specific electric field that is at a specific frequency. This is what we call a narrowband situation, and this is what we call a broadband situation, and is related with the resolution bandwidth you are using in your analysis. So when you go to the laboratory, remember, you put the device under test. At 3 meters, you put the antenna. You measure how much is the specific electric field at that distance in this specific frequency range. And if the emissions are over the limits, over the regulations, you cannot sell the product. So the designer needs to work with the prototype to reduce these peaks below the limits. How much? It depends of your company. No, for very small companies, typically they want to be exactly below the limit because this is easier. And for big companies where they have experience in EMC, they usually try to put the emissions perhaps 10 dBs below the limits to be sure that in production the product will be failing. Please, can you mute your microphone? Can you mute your microphones, please? Okay, thank you. Well, when looking for this kind of emissions, we can use near-field probes. Remember, near-field probes, basically magnetic near-field probes, are small loops like this one here that are able to pick up magnetic field from the activity in your circuit. So with this kind of tools, you can scan small PC boards or big PC boards. You can scan cables, looking for aggressive wires that can be working like antennas, or you can scan for leakage in enclosures and metallic boxes for your products. You know? What is the possibility to use this kind of probes or the scanner for debugging? The idea is that in the EM probe, you have the possibility to use one of these handheld probes in this robot with one arm that is able to move around the PCB. And this is especially useful when the product has different heights and is not a flat design. No? In the right side, you can see the EM scan. The EM scan is a flat scanner with a lot of near-field probes that are electronically switched, and then you can put your PCB or your system on top of the scanner, so you are able to see how is the activity. We will see in the demos how is the difference between using a handheld probe or using some kind of scanner. The idea about the EM scanner is instead of using one probe, we will be using a lot of probes, close to more than 1,000 probes in this flat surface in 2 different orientations, and the device under test is on top of the scanner. So we are able to do basically 2 important things. We can do a spectral scan, this one. The spectral scan is useful to identify what frequencies are in the area of your circuit. So when you are failing, for example, at 300 megahertz, you can scan the circuit and you can see that the emissions came from your device under test. With a spatial scan, what you can do is to identify in your circuit where is the activity especially located. Is close to the microcontroller, is close to the edge of your board, is close to some specific connector. Then you can do changes in real time, and you can see how the design changed in the creation of this energy of this activity. This is useful, for example, to find the source of emissions. We can identify critical loops. We can evaluate if we have problems or not very good layout designs. We can test for issues in cables, in shielding, and in general to evaluate your product. One of the important things about these kind of tools is that with these tools, you can see the signals. And remember that in general, in EMI troubleshooting, if you can see it, you can fix it. This is one of the most important things about using instrumentation for debugging EMI problems. This is the idea of working with the scanner. You need one spectrum analyzer, and the spectrum analyzer is connected to the EM scanner. Obviously, you have a software that is included with the scanner that is connected to the spectrum analyzer, and at the same time, the software is connected with the scanner to be able to switch the different probes that we have here at a specific speed and to cover the area of interest for the user. The bandwidth of this kind of scanner is very wide. It's typically from 50 kilohertz to 8 gigahertz. I think this is a wrong number. It's 150 kilohertz to 8 gigahertz. We have very sensitive antennas down to minus 135 dBms. And the area of the scan, you will see later, is around 21 times 31 centimeters. We have a very high resolution, and if you are specifically interested in applications with high resolution, there is another model of EM scanner that is for that kind of application. What can you do with the scanners? With the scanners, you can test how is the PCB in your product is working, how the PCB in your product is working. You can test cables. You can evaluate big surfaces, moving the scanner on top of these surfaces, or you can scan specific boxes or enclosures. The scanner with the arm of the robot is a different idea. Is good for situations where you have a 3D structure. This is specifically for a full product, for example, and you put one handheld probe in the arm of the robot, and then the robot will be moving the probe around the circuit in the area that you specify in the software to pick up the signal in the same way. The software is the same for both scanners, so it's very easy to use and to control the different functions of the software. Well, let's go to the demos. That is, I think, the best part. Let me see how I can. Okay, let me see how I can. Let me see how I can disconnect the screen. How it is. Okay, let me switch this off. This way. Okay, let's go to the screen and let me show you how is the PCB I will be using. This is the PCB I am going to use in my setup. This is a PCB where I have a display, I have a microcontroller, I have several keys, I have some kind of logic, I have a connector where I have the power supply. The power supply is 5 volts and it's coming from this PC board. This is a a small PC board with two DC-DC converters. This is a 5 volts DC-DC converter. This is a 12 volts DC-DC converter. And we'll be using only the 5 volts power converter. And the input voltage is with this cable here. And I am introducing here around 9 volts from my power supply that is here on top of the table. Okay, so when I switch on the circuit, 5 volts appear here, and the product is turned on. Let me try so you can see the effect in the display. I'm going to switch on, and then you can see that the display starts at this moment. No. So what kind of problem we can find in a real application? Let me show you with my oscilloscope. This is the output of my oscilloscope. I have an RTO. Okay, let me see. Where is this one? Okay, and this one. Okay, this one. This is the screen of my scope. This is time domain signal. So you can see with my camera. Let me move the camera so you can see. Okay, let's see. Whap. This is the scope, is the instrument that I have in the top of the screen. Let me adjust the focus so you can see the instrument in a better way. Okay, so I have one scope where I have 4 channels. So what is in the channel number 1? In channel number 1, let me disconnect this coax cable. In channel number 1, I am going to connect a small antenna. This is my antenna. It's a small dipole, obviously. You can, this is the equivalent to the antenna you put at 3 meters from the device. I am going to put the antenna close to the circuit so we can introduce the signal from the antenna in channel number 1. So here you can see the time domain signal that is coming from my circuit. The circuit is on at this moment. So at the same time I see the time domain signal, I can try to see how is the frequency domain. So let me do an FFT from DC up to, for example, 300 megahertz with a resolution bandwidth of perhaps 300 kilohertz in this signal. And then you can see in the top of the screen, you can see the time domain signal from the antenna. And in the bottom, you can see the frequency domain from DC to 300 megahertz. Obviously, because I am not working in an anechoic chamber or in a sealed chamber, I see the noise that is in the environment. So if I switch off my device, let me switch off the device, you will see that this is the noise I have in my environment. When I switch on again, you can see the signals that are created by my product. You can see specifically in this area around 120 something, 25 megahertz, these mountains appears and disappears when I switch on and I switch off my device. Obviously, in a semi-anechoic chamber, these frequencies, for example, this area here is from the FM broadcast band. Let me increase the size of the screen so you can see better. This area here is 88 to 108 megahertz. This is a FM band. And this is the area where I am creating noise. For example, think that with these emissions, let me switch on again. And this is the signal that I am creating with my circuit. Consider, for example, that these emissions are creating a radiated problem, and I am out of the limits, over the limits in these specific frequencies. But this frequency is a broadband emission, and it's around 126 megahertz. Where is the origin of this signal? We have one possibility to find this problem that is very useful, is to use a near-field probe. So, for example, I will be using this near-field probe. It's a magnetic near-field probe that is shielded electrically from ComPower, and you can connect the probe with this 50 ohms coax cable to the channel number 2 of my scope. Let me connect to channel number 2, and then let me activate channel number 2 in the right side of the screen. Let me increase again the size of the screen. And then let me do the FFT of this signal up to, again, 300 megahertz and with a resolution bandwidth of 300 kilohertz. And then in green color, we have here the spectrum frequency of the signal from the probe. Look at this. The output of the probe is now close to 0 because the probe is not close to any circuit. With a near-field probe, what you can do is to go close to the circuit, and then you can scan the PCB. You can scan the wires looking at specific areas where the origin of the problem is coming. So for example, if we are interested in the 126 megahertz, we can see that as we go close to the DC-DC converter, in the area where we are interested, emissions increase a lot. So this is a very nice tool to identify that the problem is coming from the DC-DC converter, and then we can apply some solution and we can try to solve the problem. Obviously, many people, I am working with near-field probes many times, find in this tool a very, very good instrument to understand or to solve EMI problems. But let's switch to the EM scanner. What is the EM scanner? As I have explained previously, the EM scanner, I will start with the flat scanner. The scanner is connected to the spectrum analyzer and is connected to the computer with the software, the EM viewer software. So let me connect the output of the scanner to the spectrum analyzer, the cable, okay. Now, let me change the camera to show you the scanner in this way. Yep. Okay. And then the instrument that is connected to the spectrum analyzer and is connected to the computer give me the possibility to open the EM viewer software. Let's go to the EM viewer software here. This is the software from YIC. Let me select the scanner of interest for me. Now the software is looking for the scanners. Wait a moment. Something is wrong here. No. What happened here? Let's try. Okay. Cancel. It was, sorry. Okay, cancel. Let's go here. I am using a Rodan Swar scanner, and I have the possibility to select the two scanners, the EM probe, the one-armed robot, or the flat screen here. Yep. Okay. And then I have the main screen of the software. Let me reduce here so you can see the circuits at the same time. The first thing to do is to specify in your project what kind of analysis are you interested in doing. For example, from the different analysis I can do, I am going to start with a spectral scan. When I select the spectral scan, I have the possibility to specify in what frequency range I am interested. For example, I could be interested from 10 megahertz up to, for example, 300 megahertz, like in my previous analysis with near-field probes. The resolution bandwidth will be, for this experiment, 120 kilohertz. So if you reduce the resolution bandwidth, you will have more frequency resolution, but the sweep of the analysis will be slower. No? We can go from 30 hertz to 10 megahertz. Okay, so let's go to 120 kilohertz. I'm not going to measure the peaks. Let's do this later. So we will be able to identify what peaks are over some specific limit. And now we need to specify what kind of probes I want active in the scanner. No. So if you look at the picture of the what happened here. Sorry, but because I have a lot of instruments connected to my computer, sometimes. Let me see if I can switch off some instruments to avoid this kind of situations. What happened here? Okay, sorry. I don't know why this is happening. Let's start again. Cancel. Let's go again to select the EM scanner. Okay, perfect. Set scanner. I forgot to set the scanner type. Sorry. I forgot to establish this scanner. Okay, now I hope now will be correct. I add the node spectral scan from 10 megahertz up to 300 megahertz with a resolution bandwidth of 120 kilohertz. Let me remove the measure of peaks and let me select the spectral scan probes. What is this? With this, sorry, let me reduce the size of the screen here. Okay. And let me open again the settings. Okay, we are, remember, from 10 megahertz to 300 megahertz, 120 kilohertz in bandwidth, no peaks in the analysis, and the spectral scan probes. If you see, now I have in green colors the cells that are active. No, let me unselect all the probes, and you can see in the picture how is the scanner. The scanner has rows that are specified with a number and columns that are specified with a letter. So you can see that if I am interested in encasing in scanning this area of the scanner, I want to specify the area from the P6 to AF6 and from P16 to AF16 if I am interested in specifically this area. Why this is important? Because if you activate all the probes, you will need more time for scanning the full area, and this is not necessary. No. So, for example, for scanning for spectral results, you can go in this area, this one. Oh, what is this? I hope something is okay. Instead of you can do this. You can select all these cells, but this is not necessary for the spectral scan. For the spectral scan, is only necessary to take some of these probes, for example, in a random way in these areas, and then you can adjust the amplitude. You can introduce an external amplifier if you want, a low noise amplifier. This is specifically useful if the signals that are radiated by your product are very small, and you can introduce some kind of description for this analysis. So now I have fully specified the spectral scan I can do in the area that I have selected. Remember, only the area where I have the microcontroller. So now I can run the scan. You will see that the scan is fast. Is setting this now. The system is setting the spectrum analyzer. Is scanning, and then you can see how is the activity of my product. I can see some specific frequencies. You can see these frequencies, narrowband results. You can see this broadband result. Look at this, is close to the mountain I was radiating to the antenna, and some specific activity here. But what is coming from my device and what is from the environment if you don't have a shielded area? Obviously, I can switch off my product and I can repeat the scan. I am going to repeat the scan, but now with the product off. Let's start, and you will see that I have now a similar result. Okay, I have a similar result, but it's not exactly the same, no? So this is with the device under test on. This is the same with the device under test off. We can see that in the scale options, now the scale is automatic. Let's go to specify a manual scale, no? Let's go from -5 to 25, for example, for the measurement with the system on, -5 to 25, and for the second measurement, the ambient noise, we put the same values from -5 to 25. So now it's really easier to compare both results. This is with the device under test off. This is with the device under test on. The only difference in the results are in this area that is close to the FM band. So this is radio from broadcasting stations. We can create some kind of a spectral comparison result. So we can put here, and we can put in the reference view, for example, the results from the ambient noise. Put here. Okay, let me reduce the size of this screen. Okay, so in the reference view of the comparison, we put the measurements with the device under test off. Now in the test view, we can put the results when the device is on, and then with the test view and the reference view, we can see the comparison. You can see that in the comparison view, we have the test view without the signals from the reference view. So the FM band disappears here from this second measurement. Obviously, you can repeat, we can repeat the measurements activating the option of measuring peaks. Remember, measuring peaks, how many peaks? For example, 4 peaks. So when we apply this and we run another test, let me run another test. Oh, sorry, this one. Let me run another test. The idea is that, let me switch on the device. Now the system is scanning the circuit, and you can see that again, the results are very similar, but the system now is detecting peaks. The measurement is finished, but now the system is detecting peaks that are over some specific limit that you can specify. For example, this one. Okay. Now you see these small circles. They are the peaks, and then we can export this information, all peaks, to some file. For example, let me call this file peaks. It's a text file. You can export all the peaks or all the data if you want to import to some spreadsheet or something like that. And you can see that from my device, I have detected peaks in 1106 megahertz, 33 megahertz, 55 megahertz, 77 megahertz, and only 4 peaks because I selected 4 peaks for measurement. And you can see that this is 11, 33, 55, 77. So it looks like the different peaks are multiples from 11. This is something like the main harmonic, the first harmonic, and the second, third, the third, the fifth, and the seventh harmonic of the first signal. Okay, we will understand now specifically why this happens. So now we know what kind of frequencies are coming from my device. And because these frequencies are coming from my device, if one of these frequencies is of interest for me for any kind of application, in EMC for conducted emissions, in EMC for radiated emissions, I can run another different scan test that is called the spatial scan. So let's, for example, say that we are interested in the first harmonic, 11.064 megahertz. This frequency for us is very important. It's creating some kind, for example, of conducted emission problem, and we try to find where the signal is in my circuit. So I add a node that is a spatial. Now we can go inside of the spectral or outside of the spectral scan. Let's go inside of the spectral. You will understand now why. And I can specify a spatial scan. This spatial scan is inside of the spectral scan. In this way, directly, I am going to test in my system for one specific frequency that you specify here in the center frequency, but because I am doing inside of the spectral scan, I can select one of the peaks that I have detected in my previous measurement. For example, I am interested in 11.064 megahertz, again with a resolution bandwidth of 120 kilohertz. And now in the spatial scan probes, instead of the probes that were randomly selected, I need to specify the full area of the circuit because I am interested in the situation of this signal. Okay. I have no external amplifier again, and I am not going to introduce title or description for this test because in this way we don't need to take more time to prepare the experiment. No? Now you can see that I can run the test. Oops, run the test here. Now the system is scanning. The idea is that the system is scanning from the first cell to the last cell, going to in all of these cells. You can see the result. In red color are the areas where we detect higher magnetic field. It's the areas where you have a stronger current, and current is typically in EMI the origin of the problem. You can see that I have some kind of loop here, and I have some kind of activity in the edge of the board. This board is a 2 layers board, and I have a specific activity at, remember, all these signals are at the frequency I have selected, is 11064 megahertz. Let me do a small change in my circuit. I'm going to do a small change, and later I will explain you what change I am doing. Let me do to introduce this component in the circuit, something like this, and let me scan again. Okay, let me make a zoom here so we can see better the circuit. Okay, this is the second. This is the first one, and this is the second. But they looks like similar, but the idea is that by default the scale is automatic. So let's go to the scale option, and let me specify a specific limit, for example, from -5 to 31 or 30. From -5 to 30, this is without the change. Now let's go to the second, and let's specify from -5. Oh, sorry, I am losing the connection with the scanner because I have 3 or 4 cameras, the speaker. Okay, -5 to 30, and you can see the difference. Okay, this is without the change, and this is with the change in the same scale. So it looks like the activity has been reduced around 10 dBs. Why is this happening? Okay, let's go with the camera close to the circuit here. You will see that if we go close to the circuit, we have here this area where I have in the microcontroller, we have the clock circuit. Okay, so you can see here. Let me see if I can make a better zoom. To zoom. Okay, you can see that this is 11.05992 megahertz. This is the main clock, the crystal that is using the microcontroller to create the main clock of the system. Okay, let me reduce the remove the zoom. Okay, sweet. So this is the area where I have high frequency activity created by this clock. Let's go here to this test. Okay, so this is the area where I am creating this activity. One possibility to identify specifically in what part of your circuit is you are creating this activity is to import the overlay. Let me open the overlay. Okay, let me open the overlay, edit overlay, and you can import here a file that is in one of my folders. And what is this? This is the Gerber file from my PC board. So we can introduce here the Gerber file, play, okay, or we can go to the second one. You can create in the main node, so you don't need to repeat this for any of your measurements. But because I have not done this before, I need to do this 2 times. But this is not necessary. You can do this only 1 time from the main node of your circuit. Apply, okay. So we can see the results of my measurements, and with the mouse, I can increase or decrease the visibility of the silk screen, okay? So we can see that this is the microcontroller, this is the clock, and this is the loop that basically I am creating. How is the change I have done to go to this situation? I have introduced the decoupling capacitor. The decoupling capacitor for this microcontroller has a wrong position. It's very far from the microcontroller with a very big loop, but the difference between the availability of the capacitor or not is really well appreciated. No, okay. So it's very, very interesting to see where is the activity of your signals. Look at this. In the edge, in this part of the edge of the PC board, I have additional activity of the 11.064 megahertz signal. I can see the result. I can see the result in 3D. So for example, we can activate the 3D and we can see how is the loop where I'm looking at the signal. No? You can see that this is the area where I am creating the loop. I have some specific activity too in this area. So perhaps you will be able to create crosstalk to other areas of your circuit or something like that. The PCB is very small to radiate 11 megahertz, but perhaps if you go to the higher harmonics, you can create problems, no? So you can see how is the activity really nice in the circuit. Okay, let's go to see what happened if I am interested in the full picture here. Instead of scanning let me introduce another spatial scan. Let's go from, for example, I'm interested in, let me go to another different scan. So you learn other option of the software. Instead of spectral or spatial, let's go to a spectral spatial scan. What means spectral and spatial is that you are going to sweep in frequency and in location in the cells you are activating, so we can see for the full frequency range and for the full PCB where the activity is more important. I'm going to scan from 10 megahertz up to 300 megahertz. Let's go to a resolution bandwidth of 300 kilohertz to go faster, not activating the measurement of the peaks. Let's activate the spectral spatial scan probes. You can see here, let me show you the picture. You can see here that now I need to scan more areas, no? So here I'm going to unselect. Let's select the area where I have the microcontroller board. Let's select the area where I have the DC-DC converter, something like this, more or less. And let me select the area where I have the power supply cable. This area, more or less. This is the area of interest for me for my scanning. So let's accept and let's run the spectral spatial scan now. I am going to save the circuit. Let's go to demo. In case my computer is resetted or something like that. Now the system is scanning, and you will see that now the system is scanning continuously in the full frequency range and for any of the cells we have in the circuit. Now I have the decoupling capacitor connected in the microcontroller board. You can see how in the left side you have the sweep in frequency for any of the cells I am activating. Okay, you can see it depends on the frequency range, the resolution bandwidth, the number of cells that you are going to activate, that the sweep is faster or is slower. You can see that in frequency, we start to see a mountain in the area of 125.26 megahertz. This is the area that I was radiating in my first measurements with the scope and the antenna. So in some area of my circuit, I am creating this electromagnetic energy. Oh, sorry. Okay. Do you look at the red color? Looks like the 125, 126 megahertz is not coming from my digital circuit. Okay. Oh, sorry. I have a lot of USB hubs, and sometimes Oh, aborted. So let's go again. Let me change to do this faster. Let's go to, no, 300 kilohertz. Let's go again. Let's try again. I hope the scanner will not be disconnected again. Sorry, I have 1, 2, 3, 4 cameras. I have the headphones with wireless system, another camera for the conference. I have the scope, the Rodan Suarez scope. I have the spectrum analyzer. So it's a lot of things connected to the computer using USB hubs. And you know that Windows and USB sometimes create these kind of problems, especially if you are doing some demo. Okay, let's see if we are able to scan without problems again. Okay. Anyway, you can see that I have strong activity at 126 megahertz, no? Oh, why? Why? Let me try again. What happened here? I don't know why the scanner is. Let me try to connect to other. Let me try to connect to other USB hub. Sorry. Okay, I have changed the USB hub, so perhaps we are more lucky. Okay, we start again. Sorry for the inconvenience. Okay, while the system is scanning, let me show you the overlay I will be opening. Instead of using the Gerber file from your PCB software, I will be using a picture that you can take with your camera. Let's open PowerPoint, for example. So I can put here the picture. No, you can take a picture of your prototype. In this case, I have taken a picture of the cable with the DC-DC converter and with the microcontroller board. And when the system finishes the scan, I will be importing this overlay. So instead of working with the Gerber file, I will be working with a picture of the system. Sometimes this is useful in case you don't have the original files of your system. This looks like it's not stopping the scanning. Sorry, but this is the first time the scanner is disconnected. I have been using a lot of hours without this problem. So sometimes the order you use in switching on your devices in the computer create this kind of problems too. Okay, now we are with the area of the DC-DC converter. Now it's working better with the other USB hub. Okay, so you can see it's finished, and you can see here how is the activity. When you put the mouse on top of the different cells, the software gives you at what frequency this activity is higher or lower, no? So for example, if I go on top of the red color, let me make a zoom here. Oops, sorry. Preset zoom. If I make a zoom here, you can see that the area that is in red color is the area where I have the DC-DC converter, and is the frequency of 126.9 megahertz. No, I can import the overlay, edit overlay. We can import, remove this one, and we can import, instead of the Gerber file, we can import the picture. So you put the picture here, and you can change the size to accommodate to your scanning area. Okay, more or less. I will not be very, very precise. Okay, so now with the mouse, you can change how is the visualization of the picture related with the scanning of the area. And then we can see, let me increase the size of the screen. We can, sorry, this one. We can change the 3D view. Okay, so we can see in what area of the DC-DC converter I have the specific activity, no? This is the area where I have the inductor and the transistor of the buck converter. No? This is the area where I have the strong activity. But in any way, you can see that I have some kind of activity. Let me remove some kind of activity of 126 megahertz is in this cable. No, we can repeat the measurement introducing some possibility of filtering the noise. Let me go to the camera. The noise in this cable. If 126 megahertz goes to this cable or goes to this cable, the cables can be good radiators, no, good emitters. So let's try how is the difference in this position when I introduce a ferrite. I'm going to use a Würth ferrite. Let's show you the ferrite I will be using. This is the ferrite I am going to use. It's a ferrite that at 100 megahertz is around 182 ohms, no? So you go to the specific graphs from the Würth Electronics, you will see that the impedance in ohms has a maximum of impedance with 1 or 2 turns, basically when I am between 100 and 200 megahertz. But I am going to take only 1 turn, not 2 turns, no? So now let's go to the picture so you can see what I'm going to do. I'm going to introduce the ferrite in this position, okay? You can see my ferrite to reduce the common mode noise in this cable. So I repeat the test. No? So now the system will scan again. Remember that if you have a cable and the 2 wires in the cable are one close to the other, usually differential mode currents will not create a problem for you. But common mode currents, the current that goes in the same direction in the 2 wires, have an uncontrolled loop, and around 15 to 20 microamps of current circulating in your cables can create strong radiated emissions. And then that is because many people typically use a ferrite in cables when they are failing in radiated emissions. This is not a good solution in some products because I don't know the cost of the product if you have manufacturing a lot of units or something like that, but it's a very nice and fast solution when you need to go to the market quickly. Okay, let's go. We have the emissions in the converter in red color again. You can see that the emissions at this specific frequency start to go down because the energy is here, but it's not able to go through the cable to the other PC board. Now we will see the difference comparing the results. Wait a moment, it's very fast. Okay, this way, the DC-DC converter. Now the scanner is not being disconnected from the computer, fortunately. Okay, so you can see the difference between this and this. Let me put the same scale, no? For example, in this scale, I am using from 8 to 45 in the limits, 8 to 45. So let's go to the other measurement with the ferrite from 8 to 45. So with the colors, and you can see the difference. When there is no ferrite in the cable, part of the energy that is created in the DC-DC converter can go to the other area. So the full system can radiate 126 megahertz. But when you put the ferrite in the cable, you can see that the 126 megahertz signal is here. Obviously, it's created here, so the ferrite here don't change the possibility to create, but the energy is not able to go to the other PCB. If you go with the pointer on top of the different areas, you will see the frequency that is in red or green color. No, so for example, this is the frequency in red color here is around 127, 126 megahertz. But if you go to this green color, you will see that the frequency is the harmonics of your signal. You can use the full user composite view or the user composite view to identify from one of the measurements, spectrum analysis to the spatial analysis, where the signals are. For example, let's go to this area, and I am interested in knowing where this signal is. And then I go to user composite view. If you click here, you see that these frequencies are here. But for example, if I am interested in this frequency, it's here, okay? If we go here, we can see that the frequency at this signal here is in this area. This signal here is in this area. And the opposite, if you use the user composite view, you can say, where is this? What is this? This is basically this frequency. So you can identify from the spectral analysis and the spatial analysis from one to the other where your signals are introduced. Okay, so we have been using the flat scanner. I'm going to change to the other scanner. In the other scanner, sorry, I'm going to use the EM probe, set scanner type, and now I will be changing the connection of the radio frequency. I'm going to disconnect the radio frequency from this connector, and I'm going to connect to the output of the near-field probe in the scanner. Let's show you with the camera how is the scanner, how is the EM probe. Okay, so let's go to this. Okay, this way, and let's make an auto zoom. And I'm going to remove the probe from the robot, so we can see that in the software, the first thing that the software is inviting for me to do, oh, sorry, what's the problem? I don't know why this is happening. This is the demo. Oh, sorry, this one. Let me show you. This is not the file. This is the file, TV. This is one. Oh, sorry. This is the, I have another window in the back. Where is the, okay. Where is this one? Hop. Okay, let's open again. Okay, now the software gives me the possibility to remove the probe, and then the robotic arm will be doing some kind of homing action. So you can see in the camera, let me show you the camera, and you are going to see that the first operation of the robot is to find a reference position. You need to remove any kind of object that you have around the area where the robot is moving. And I am going to scan a full product. This is a TV set box. So you can see that I have a PCB, I have different connectors with different heights. I will be interested in scanning this area. So I will be showing you the possibility to evaluate how good or how bad is, let me see if I can make a zoom, how good or how bad is a silt around this area in the PCB. Okay, I will remove or I will put the cover. So let's go to introduce the probe now. I'm going to introduce the probe. Now we have the probe in the system. And now I show you the spectral spatial scan probes. You can see again, I have, like the overlay, I have a picture of this as part of the system, so it's easy to identify how is the difference. Now the probe is here, where you see this cross, but I will be testing here. And the spectral scan probe position, let me put here -22. You can get the position, now it's in position 5. Now I am going to specify, oops, sorry. I think I have some small problem here. Oh, sorry, let's wait a moment. It's not responding. Okay, let's disconnect. Okay, let's open again. Okay, I need to do again the zero in the setup. Let me remove the probe. Let's go to make the homing action. Okay, and let's introduce the probe again. 1 second. Okay, let's go to the file, open, TM probe. Okay, let's go settings, spatial, spectral, minus 25, 22 is the good height. Settings, spectral, minus 22. Now let's go to the height manually. In this position, let's try to settings. Okay, now I am at the start, and this is the position is minus 25. Let's put minus 22. Okay, minus 22. No, this one is minus 24. Accept, and then I can run the spatial spectral scan. You will see in the picture with the camera how the probe will be scanning the circuit. Oh, sorry, it's very high. The probe. Stop. Sorry. I don't know what happened here. I don't know why this is happening, really. I have never experienced this. Accept. Okay, let's try to open this one. Settings, spectral spatial, get probe position is 5. Now we will put this manually. Get probe position, minus 25, correct. Let's go again. Now you will see the probe in the bottom right picture. Okay, now it's working. So the idea is that the probe is scanning the area with the height you say or you specify. You can specify with a file different heights. Now the system is scanning, and you will find that there is a specific activity around 90 megahertz. It's coming from this area in the PCB. We can do a zoom here, okay? And we can see the areas where there is more activity at some specific frequency. This is the situation without the shield. And this is the emissions from the product. Now we can put the cover if you are interested in evaluating some shielding material, for example, or some mechanical design of your shield with holes, with slots, with seams. No, I have several slots here. Then I can repeat the scanning of the circuit. You can perhaps be interested in looking at the difference with some ferrite absorber. Okay, so we can scan. I stop it again. I don't know. Let's wait 1 minute. And if not, I think we will stop here because I have some problems with my USB ports. And I need time to solve it. Okay. Let me switch off again. Okay. I don't know why this happened. Wait a moment. If not, I will. Okay, you can see in this picture that the amplitude of the signal is around 35, for example. The idea is that if we scan again, let me try this, accept. Wait a moment. Now it's in position again. And then settings, scan probes. No, something is wrong in my computer, sorry. I don't know why it's not responding. Okay, I hope you discover how is the technique. So sorry for the inconvenience. Sorry for this demo option. You know that in MATLAB and in PowerPoint, all is easy to work. And when you are working with demos, this lot of tools connected to the computer, sometimes this happens. So I will be happy to answer any questions or to repeat some of my measurements if you want. Let me know any question you have about the system or about the techniques.